All right. Hi, everyone. Now we are moving to block 2. I call this block operating envelopes as business as usual. I'm not sure where that's the best title. Throughout this workshop, we're going to discuss the need for better approaches. We're going to discuss about forecast. You have seen in the presentation from Alex that they need to make assumptions, and even presentation from Liam, they are using really weather forecasts and things. But of course, forecast needs to be improved, and there are many things that we haven't really forecast in the past. We're going to discuss that. We're going to discuss the role of data-driven approaches. We will have an interesting presentation about model-free operating envelopes. We will discuss about flexible imports. All right. So there was a little bit of discussion, with Alex as well with Liam, but what is this? What is the flexible imports, and what are the challenges that we're going to have there? So we're going to discuss that a little bit, and then we will finish as well with how are distribution companies here in Australia justifying the investment in operating envelopes, right? So we will learn a little bit about the CECV methodology. I will tell you all about that, and we will finalize the block with a small discussion about well, what happens next really is operating envelopes going to be this fantastic solution that means we are not going to have more poles and wires being upgraded. So we're just going to stay with the same infrastructure. Well, spoiler alert, no. Okay, but we will discuss that. All right. So that is the idea of this particular blog. So let's start. So as I was mentioning, we're going to discuss the need for more accurate approaches. Then we're going to move to model-free operating envelopes. That will be a presentation from Vinny that he will share his screen. Then we will come back to flexible imports. What are the challenges? We are going to justify investment, discuss that, and we will finalize with network augmentation. The idea here is really not to tell you, okay, this is it, and this is what needs to be done. This is really to complement everything that you have been learning so far. You have learned about the concepts, some simulations that really bring very interesting points to your attention in regards to the exports, the operating envelopes, the benefits, the challenges. And you have seen as well what is being implemented right now in Australia, in states of Queensland and South Australia. And very exciting, but still, there are still many challenges and many things that need to be improved. As usual, it is a never-ending job to do things better. All right, so let's move first to the need for more accurate approaches. So what I mean by that really is to look at certain aspects that we were discussing that were, let's say, not necessarily quite up to scratch, right? So these are two slides that I took from the presentation yesterday that was in blog 1. And these were the forecasts that we were discussing super briefly, that were used in Project Edge. And the forecasts were not necessarily that great, right? And of course, the moment that we have poor forecast, the calculation of the operating envelopes is going to be poor, and the network could be compromised, or customers might be over-constrained. So that's not great, right? Of course. However, we need to understand that forecasts for operating envelope calculations, particularly in the low voltage part, are not easy. So this is not about saying, oh, forecasts are terrible, we need to do better. Yes, we need to do better, but it hasn't been done anywhere in the world, actually, as a matter of fact. So let's reflect on that. Forecast calculations for operating envelope purposes are not easy. Okay, why? Because it is a totally understudied field, all right? When we talk about forecasts and customers, it is energy. Forecasting energy, the amount in a given time, is easy. Forecasting power at a specific time is very difficult. So, for instance, here you have a plot here. This is part of the ongoing research from Fernando at the University of Melbourne, Fernando Lanas. And you can see here in this plot 30 houses how the aggregated power looks like. That's easy to forecast to some extent, but one house, totally different. It's a very, very different game. Let's look at reactive power. Again, in the aggregate, it might look like something that is forecastable, right? You can see a trend, a pattern. An individual house, a totally different game. So, active power forecast of single customers hasn't been done. Typically, it's done for thousands of customers, right? And right now, distribution companies that have smart meters, they're doing it per transformer, but still, we're talking about hundreds of customers in some cases. Voltages of, or forecast of voltages at the distribution transformer that are needed if you want to assess more or less what are the implications of exports or imports on customers as a proxy, just using the transformer, or to run power flows if you need that as well, as we were presenting yesterday. Well, hasn't been done, right? So in the past, we haven't needed that, and then therefore people were not looking at this. So we need methods that actually are applicable to this type of inputs that are required for the operating envelopes, all right? Now, what does this mean, all right? So we need to look at different methods, and there are different methods, okay? Forecast is something that has been done already for many, many decades for different purposes, all right? The most obvious one is the weather forecast that we have in our phones, right? But this is a different type of forecast with different type of purposes. And it matters. It matters that we understand that active power is different from reactive power and different from voltages. This is just a little plot that I'm gonna present on the right-hand side right now. It's not there with some results, but this is considering one of the project edge sites, just 8 customers, just 12 spring days, actual data from the particular site, multiple features considering radiation, temperature, humidity. As you would do forecast, you have more features as well to make the forecast more robust. And in this case, we're going to consider the equal allocation operating envelope. I'm going to present just the results just to give you a sense of what different forecasts will actually give you results. So what you see in the plots there, these are violin plots that are just showing, what would be the effects on customer voltages of using operating envelopes with different forecast methods. Looking at the active power, looking at the reactive power of customers, and the voltage at the transformer. And I'm not going to go into the details because it's quite heavy plots there. But if you look at the different violin plots and also how they exceed the 253 volts, which is the upper limit in terms of voltages, you will see that different methods have different performance. All right. And what can work very well for active power or pretty decent, all right, might not necessarily work for reactive power and might not necessarily work for voltages. So this means that it is very likely that we will need different methods of forecast for the different inputs that we need in the calculation of our operating envelopes. Now, this is important because, of course, traditionally we will just kind of use methods that are very well established. We need to do the corresponding research. And well, fortunately, we're doing some of the research there. Moving on, let's talk about data-driven construction of low voltage networks. So can we, just using only smart meter data, construct 3-phase low voltage networks? So we're talking about topology, phase groups, impedances. And we were talking yesterday that actually it's very difficult to put them together, right? Project Edge was taking weeks, in some cases months, because of the visits, that they need to go and check visually and multiple iterations in terms of what is working, what is not working. Well, the answer is yes, we can. This is part of the ongoing research by Eshan, the University of Melbourne as well. And what we are showing you here is the original topology of a validated project edge site here on the left. So we know the phases, those are the colors there that you have in the circles. We know that the topology and we know the impedance. Just using smart meter data, we were able to construct the topology, nothing else. Now, with using smart meter data and very sophisticated approaches, it is possible to really match the topology of the validating network from project edge, where people needed to go and check and everything, a lot of time for that. And it was possible to match the phase groups. Interestingly, we were able to improve the impedances. The impedances with this technique actually were slightly different, and they were improved. Now, at this stage, you might argue, Nando, how do you know you're improving? You are just having different values. Well, because we can run power flows. We have the model, and we have the historical data from the smart meters, so we can compare. So the results of the match between the calculation of voltages and what was recorded by the smart meters is much better with the improved impedances. So what I'm trying to say here is that it is possible to do this. Now, there's a caveat. There's always a caveat, right? Nothing is perfect in life. The caveat is that these sort of techniques require smart meter data from all customers. And of course, as we were listening, from what is the case in Queensland or South Australia. Not all the customers have smart meters, as it is the case here in Victoria. And even in Victoria, commercial and industrial customers, although they have smart meters, it is not managed by the distribution companies. So there are limitations, which then takes you to the question of, okay, so but what can we do if we have partial smart meter data? Well, this is where we're gonna discuss the model-free operating envelopes. Vinny, you can share your screen now.
So can you see my screen in full mode?
Yes, we can.
All right, perfect. Hello everyone. My name is Vincenzo Bassi. I'm a co-founder and the CTO of VoltMind, which is a startup company, a spin-off from the University of Melbourne that aims to provide software solutions for the electricity sector. I'm also a PhD candidate at the University of Melbourne under the supervision of Nando. And I'm here to talk to you about model-free operating envelopes as was introduced by Nando before. So in a nutshell, as it was discussed yesterday, the ideal calculation of operating envelopes requires power flows and consequently electrical models, which for low voltage networks in general are not really available for most distribution companies around the world and can be challenging, time consuming and costly to produce. So as Alex and Liam were discussing in the previous blog, we need to come up with some alternatives. And what I'm going to discuss today is an advanced alternative method based on smart meter data and artificial intelligence to calculate DOEs without the need for electrical models. So as an outline of this presentation, first I'm going to present all the details of our model-free approach to calculate operating envelopes. Then I'm going to illustrate the concepts with a case study from Project Model-Free Operating Envelopes at NEMI level, which is a 2-year project developed by the University of Melbourne, funded by the Centre for New Energy Technologies, C4NET, that involved all distribution companies here in Victoria. Then I'm going to present some results from an offline trial carried out by VoltMind with Energy Queensland, which is really exciting as this our concept that we develop in a research context, and now we are moving towards a real-life application. And finally, I'm going to present the key remarks of this presentation. Please note that this presentation is intended to last around 20 minutes. So in terms of model-free operating envelopes, well, here there is a schematic of our model-free approach. Essentially, calculating operating envelopes is all about evaluating voltage and thermal constraints for different DERs, what-if scenarios, and assessing up to which extent flexible customers can import or export without compromising network integrity. So to do this, we are going to use either operational smart meter data or forecast to define customers' demands, depending on the horizon for which we are calculating operating envelopes. And we are going to define the imports and export for flexible customers that we are going to assess. If voltage monitoring at the distribution transformer is available, we can use it, but it's not a strong requirement for our approach. Once the scenario that we want to check has been defined, what we are going to do is that we are going to use a neural network that was trained with historical smart meter data to calculate customers' voltages. And we are going to use tailored approximations based on individual and aggregated net demands to assess the utilization of key assets. If everything is okay, we are going to define a harder scenario. For instance, if we are calculating export dynamic operating envelopes, we are going to increase the exports for flexible customers. And if not, we have found our operating envelopes. And the same principle can be applied for hosting capacity, for instance, and for many other applications such as DR connection request and so on. And the key features of this approach is that, well, of course, there is no need for power flow analysis or electrical models. And as well, this corresponds to an extremely quick alternative to power flow-based techniques. So in here, we have a schematic of the neural network production stage. So the approach is carried out on a per distribution transformer basis. And the first stage corresponds to the production of the neural network, which occurs offline. This part is comprised of 3 main stages. First, we pre-process the historical smart meter data. Why we do this? Well, in real life, smart meter data is not perfect and can be subject to missing or erroneous measurements due to, for instance, errors in communications or smart meter malfunctions. Once the smart meter data has been pre-processed, we go for the second step, in which we train multiple neural networks whose inputs are customers' active and reactive powers, and whose outputs are customer voltages. And we do this process to define the most suitable neural network for the studied low voltage network. Once we have defined the corresponding neural network, which can take a few minutes depending on the size of the studied low voltage network and the amount of data that we are using, this neural network is ready to be used in an online fashion to assess customer voltages for any DR what if scenario, and thus determine the operating envelopes for flexible customers. So in here there is an schematic of the online process to calculate operating envelopes. In terms of inputs, what we are going to use are the net demands, active and reactive powers of non-flexible customers. It means those customers for which we are not calculating the dynamic operating envelopes. Besides, we are going to use the net demands, reactive power of flexible customers for those it means those customers for which we are going to calculate the operating envelopes. And as I was mentioning before, these values can come from either from operational AMI data, for instance, if we are calculating operating envelopes in near real time or 5 minutes ahead, 10 minutes ahead, and so on, or from forecasts if we are calculating operating envelopes well in advance, so for instance, hours or days ahead. Furthermore, we are going to need the network constraints, which corresponds to voltage statutory limits, which comes from the regulation, and the thermal capacity in kVA of the corresponding assets. In terms of the algorithm, this is comprised of two main blocks, which interact in an iterative process to define the corresponding dynamic operating envelopes. So the first block, which is what we call operating envelope evaluation, defines the set of operating envelopes for flexible customers to be evaluated based on the allocation technique to be considered. This set of operating envelopes is sent to the network constraint assessment block, where the technical feasibility of this set of operating envelopes is evaluated. And how we do this? Well, in terms of voltage limits, we use the neural network to calculate voltages and assess if the set of operating envelopes is compliant with the voltage limits. And in terms of asset utilization, we are going to use these Taylor approximations based on individual and aggregated net demands. And we are going to check thermal constraints at 3 key points of the network. The first one is at customer connection point. The second one is at the LV conductor at the head of the low voltage circuit. And we are going to also check at the distribution transformer. And it's important to note that if phase grouping information is available, or if a data-driven method is implemented to identify this information, we can do this on a per phase basis, all right? So the first set of dynamic operating envelopes that we produce is 0 kilowatt for all flexible customers, and we keep increasing exports according to the adopt allocation technique, essentially until some network constraint is breached. Once this happens, we have found the corresponding operating envelopes for our flexible customers, which is the output of our algorithm. So to illustrate these concepts, I have prepared a case study from project model free operating envelopes at NEMI level, which, as I mentioned before, was a 2-year project developed by the University of Melbourne, funded by C4Net, that involved the distribution companies in Victoria. And in this project, we demonstrate the effectiveness of our model-free approach with real smart meter data from around 700 customers from 8 different low-voltage networks in Victoria. The case study that I brought today is related to the largest of these low-voltage networks. So, well, first of all, these slides are going to be available after the presentation. So I'm leaving here the link to our project website, where you will be able to find all the material related to this project, so which include webinars, papers, and technical reports. So I encourage you to go for it after the presentation. So, all right, so in terms of the case study that I'm going to present today, as I was saying before, corresponds to the largest low voltage network that we assess in this project, which is owned and operated by the Victorian distribution company Yemena. This low voltage network is comprised of 4 low voltage circuits and 155 customers in total. We will consider 146 after the data processing. Note that some customers were excluded from the calculations due to erroneous values. For instance, voltages equal to 0 or 100 volts through all the data, or extremely low variety in their data. In terms of the neural network production, we are going to use an equivalent to 3 weeks at 5-minute resolution. which comprise the period between November and December 2021. Please note that because of gaps in the data, like missing values or erroneous measurements, this might not necessarily correspond to 3 calendar weeks. The same happens with the test data set that we use to assess the accuracy of the neural network, which is also equivalent to 3 weeks at 5-minute resolution, which is contiguous to training and comprise a calendar period between January and comprise data between January and March 2021. So in terms of what we're going to do, first we develop the neural network, we produce the neural network, and then we are going to use it to calculate operating envelopes. So in terms of the neural network accuracy, what we are presenting here are the results of the neural network for these 3 weeks that we used to assess the results. So in the upper part, what you are seeing is the numerical results, right? So in terms of root mean square error, average deviation, and maximum deviation, we can see that we achieve an average deviation of less than 0.6 volts, which is really accurate. In the lower part, you are seeing 2 plots. In the left side, you are seeing the time series results. In these plots, what we are coloring are the regions between the minimum and the maximum value at each instance, all right? In purple, what you are seeing are the model-free voltage calculations. It means the voltages calculated by the neural network. Whereas in black, what you are seeing is the test actual voltages. And you can see that the superposition is really accurate. So for instance, I would like to highlight that at the beginning, we have like big voltage drops that are adequately captured by this neural network. In the right side, what you are seeing is a scatter plot where the y-axis corresponds to calculated voltages and the x-axis corresponds to actual voltage values. Note that the identity line in this plot is to represent what would be perfect calculations. However, due to it means calculated equals to actual voltage values. However, due to noises and synchronizations issues, we do not really expect all values to lie exactly on the identity line. Instead, what we expect are results to align with this line, which can be observed here. This means that the underlying physical relationships of the low voltage network are being captured. Overall, we can say that we obtain really accurate results, achieving an average deviation of less than 0.6 volts out of around 230 volts, which is the nominal value for this low voltage network. And we're going to use this neural network to calculate export operating envelopes. So in terms of operating envelopes, an overview of what we did, well, in terms of the consideration, we calculate the operating envelope for a summer day of 2021. The idea is that we use a day with high PV injections. We are going to consider 11 flexible customers, all with PV systems. In terms of forecast, we use perfect forecast. So we calculate what we call hindsight operating envelopes. And in terms of the allocation technique, we're going to use equally distributed operating envelopes. Please note that we use an equally distributed allocation technique, but of course, our approach can be used with other allocation techniques, such as, for instance, maximize exports. In terms of network constraint, we are going to use the upper statutory limit of 253 volts of Australia. And in terms of assets, we consider a customer connection point capacity of 14 kVA, which is a cable of 60 amps, a low voltage conductor at the head of the low voltage circuit with 211 or ish kVA per phase, and a distribution transformer of 750 kVA of capacity. In here, you are seeing the voltage calculations results for the day of interest. So we can see that they're pretty accurate. I would like to draw your attention to those 2 points that we are seeing, in which the voltages goes beyond the upper statutory limits, and we can see that the neural network is able to capture this and achieve calculation that also goes beyond that limit. In below, what you are seeing here are the equally distributed operating envelopes that we obtain. And what you can see is that we obtain consistent results. So for instance, between 3 to 6 a.m. and between 6 to 8 p.m., we are seeing that there is more voltage headroom, and the resulting operating envelopes are larger operating envelopes. So in general, what we can see is that when we have low voltage, a small voltage headroom, we see small operating envelopes. And when we have a large voltage headroom, we see large operating envelopes. And specifically in those 2 points that I was mentioning before, we can see that operating envelopes goes to 0, all right? Besides, is also important to highlight that we obtain that these calculations are extremely fast calculations. In an average, it took 1.3 seconds per instance to calculate these operating envelopes for all customers. Now, I'm going to present a case study from an offline trial carried out by VoltMind with Energy Queensland, where we demonstrate our technology in some of their low voltage networks. which, as I said before, is really exciting as this concept we're developing a research context, and now we are moving towards something more tangible in real life, all right? So a little bit of context, we have been carrying out offline trials of our model-free technology with some distribution companies here in Victoria. We complete one in December 2023 with Energy Queensland, where we trial our model-free dynamic operating envelopes technology. And we have an ongoing trial as well with South Australian Power Networks related to our model-free hosting capacity technology, which essentially is the same principle. And we are currently gearing up to offer our model-free technologies through Future Grid's Compass platform, which is an industry-leading platform for smart meter database analytics. The case that I'm going to present today is just an example of what we did with the trial with Energy Queensland. So the example that I brought today is about a low voltage network with 80 customers, from which around 88% of them have a smart meter. For this case, we use only 2.5 weeks at 10 minutes resolution of smart meter data to produce the corresponding neural network. In the upper part, what you are seeing are the numerical results, again, in terms of root mean square error, average deviation, and maximum deviation, where we can see that we obtain really accurate results, achieving an average deviation of less than 0.3 volts, which is really accurate. In the lower part, again, in the left side, you can see the time series plots. This time, the test data set that we use corresponds to 4 days, is an equivalent to 4 days at 10-minute resolution, because it was the data that we have at hand. And in the right side that we have available, and the right side, again, you can see this scatter plot where, again, we can see that the calculations resemble this identity line. So overall, we can say that we obtain accurate model-free voltage calculations, achieving an average deviation of less than 0.3 volts out of a nominal value of 230 volts, all right? So, and what we did, well, moving forward, essentially what we did in here was to calculate hindsight operating envelopes for 6 summer days with 2 different methods. The first one, which is at the left side of your screen, corresponds to Energy Queensland scheduled DOEs, which was presented by Alex in the previous block. This is a method proposed by Energy Queensland to calculate dynamic operating envelopes where there is no transformer monitoring. This method essentially uses seasonal and time of the day assumptions of the export from existing DERs to create worst case scenarios of the power flow at the distribution transformer. These worst case scenarios are used to assess the available thermal capacity at the corresponding transformer at a given time of the day, which is then used to determine the corresponding operating envelopes for flexible customers. The second one at the right side of your screen corresponds to our model-free approach, which we have been discussing throughout this presentation. And we calculate DOAs for 3 scenarios, considering an increasing number of flexible customers in the corresponding low voltage network. So case 1, which is the upper row, considers 7 flexible customers. Case 2, which is the middle row, considers 10 flexible customers. And case 3, which is the lower row, considers 12 flexible customers. And in all of them, we can observe that our model-free approach can help to unlock additional exports from flexible customers. As key remarks for this presentation, well, first, we can say that an advanced model-free approach enables DNSPs to calculate more accurate operating envelopes without the need for electrical models, just smart meter data. What we have shown in here is that our approach can help to unlock additional exports compared to simpler DOA implementations. And in other trials, we have also demonstrated that our approach can help to enhance power quality compliance. Second, we don't really need massive amounts of smart meter data. So what we recommend to produce the neural network. So what we recommend is 3 weeks at 5-minute resolution. But in these trials, we have been using even less than that. So for instance, for the case that I was presenting before, we were using 2.5 weeks at 10-minute resolution, which is essentially because of the difference in resolutions and the difference in the length of the data, essentially is around half of the 3 weeks that we were recommending before. In terms of the times of the production of the neural network, this is really fast. So the neural network is produced in just a few minutes and can be used for multiple months without requiring further updates if there is no changes in the low voltage network, of course. And this corresponds to an extremely fast alternative to power flow-based approaches. So as I was saying before, in terms of equally distributed operating envelopes, this can be calculated in a second per instance. And finally, the approach can handle partial smart meter data, as Nando was saying before. Well, for instance, in this trial, this includes transformers with around 50 to 20% of customers with smart meter data, with smart meters only. which is really important because it might be the situation of some places around the world. Finally, well, these slides will be available after the presentation. So I'm leaving here the list of our latest publications where you will be able to find papers, technical reports, and so on. And well, that will be all from my side. Thank you for your attention.
Thank you very much, Vinny. And well, I mean, questions are going to be taken at the end of the blog. So please do write all your questions, as some of them are there. Thanks a lot, Vinny. Jing, we'll move to you. So if you can stop sharing your screen.
No.
Just a second. Let me just start sharing my screen. Now we are moving to flexible import limits. All very interesting things, actually.
Just to double check, is my volume okay? My sound?
Your volume is perfectly fine, Jing. So
okay.
Just...
Oh, good. Shall I start then?
Yes, please.
Okay. Hello, everyone. My name is Jing. I'm currently a final year PhD student, also research fellow, working with Nando. So in these 2 days OECOS, we have been talking a lot about the flexible export limit. And I do see people start to questioning about what about imports. Thanks to Alex and Liam, there already have been some initiative in the industry studying how to manage these imports. So in next about 10 minutes, I would like to discuss more about what kind of challenges we are expecting for the imports and what are the potential solutions we can help to manage them. Next slide, please. So what is happening now with the imports? In the next past few decades, we are seeing some load growth, but it's steady. So it means our demand or imports are still quite within the limit. Our ports and the wires are quite good to handle those load growth. But things gonna change fast, and the electric vehicle will be the game changer. Actually, by forecast, by 2030, 1 in 5 houses in Victoria will have an electric vehicle in that form. And here you can see a very simple low voltage network, which we have already seen some in previous slides. And instead of the solar system here, we consider a scenario with a very high electric vehicle adoption. And by our observation, we have seen people start to charge their car when they return home. So it means now on top of the cooking and the heating demand, you have this extra EV charging demand need to manage. And it's normally happening in the peak hours. And which means we have a larger peak demand during those high demand periods. And which makes things worse is people are now just towards a fast charging option. So in Australia, for the single phase residential charging, we usually have 2 modes. The level 1 is normal charging of 3.7 kilowatt, and people are actually going for the level 2, which provides 7.4 kilowatt, doubles the normal charging demand. So all brings them together, we are potentially going to see a severe network issue, which include both the thermal issues on the poles and the wires, also the voltage drop issue at customer connection points. Click, please. And so in conclusion, because we are expecting potential network issues, the question comes to us, so how to ensure the integrity of distribution networks? Next slide, please. I'm very happy to tell you there's already a lot of effort has been put into the industry to understand how to manage the imports. As mentioned by Alex, there is a dynamic EVSE project going on in Queensland, and Liam also mentioned in the next 5 years also, we will start the demand flexibility trial in Japan. And here I put an example of the dynamic electric vehicle charging trial, which is led by Gemini and in collaboration with several other DNSPs, including AusNet. And in these slides, you can see an example of AusNet approach. Click, please. So what they are proposing here is in whatever critical scenario, or let's say there's overloading happening in one of the local transformer, so they need to manage the demand. So DNSP taking the monitoring data from the network, also from the charging point, using those data, they will be able to calculate a good set of the EV charging set points. So we'll be able to manage the charging demand remotely. Here we name it as the charging point input limit, which is a limit just put on the EV charger only. And overall, this charging point input limit has already been proved very effective. However, we are also hearing another voice. We're seeing there's a move towards these meter level limits, which we will also call it as operating envelope. Next slide, please. For this operating envelope, I'm not gonna repeat again for those flexible export limits, the concept, the calculation. I believe you have already learned a lot from Nando, from other instructors. So the key message here is, since a flexible export limit has already been implemented in the industry, of course, it's practical, also can be effective. Then we start to think, can we also apply these meter level limits on the imports? Click, please. Yes, so let's have a look what will happen if we apply these meter level limits on the imports. Next slide, please. So this slide is one of the most important slides for my today's talk. So I wanted to bring your attention here. Let's have a look. So similar to the meter level export limits, this import limit is calculated by DNSP. For example, at 8 p.m., which is a peak time. So this import limit can be very low. For example, 1 kilowatt here. And if considering equal opportunity, every houses will receive a import limit of 1 kilowatt at their meter level. So this 1 kilowatt will be published to aggregator, and they will be responsible to manage the assets behind the meter to ensure those loads are within the import limit. Okay, so for example, the aggregator comes to check what can be manageable, and as this customer has an electric vehicle charging at their full rate, they will be able to reduce the EV charging demand even down to the zero. So they will be able to manage the imports. However, in some critical cases, even by bringing the EV demand to zero, which is not enough, and as they start to looking, okay, is there any other appliance can be controlled? However, unfortunately, most our home appliances, they are uncontrollable. Then in these scenarios, this control action cannot be achieved. Click, please. And which is also the scenario mentioned by Alex. Apart from those controllable loads, we usually don't have strategy to manage those uncontrollable loads. And what DNSP can do is maybe just accept those unmanageable load exceeding the import limits. However, just to bear in mind that this meter level import limit is to calculate ensuring the distribution network integrity. So in this case, since those unmanageable load are exceeding the limit, we do not have ensure on this distribution network can still have this integrity be managed. So there is a challenge to implement this meter level import limits. And we start to think, if we don't control the in-house appliance, what we just apply the import limits on DERs only. It can be done as an aggregate limit of all the DERs, or it can be done by device, as mentioned by Liam, maybe just one separate limit for PV, one separate limit for EV and battery. It can all be done. I will not provide you answer directly here. What I gonna do, I will take you through some calculation demo of different type of flexible import limits, so you will have a better understanding what is going on. Next slide, please. So here is a simple calculation demo of the first limit I mentioned, most simple one, the charging point import limit. What you can see here is a small transformer which is supplying two customers. Both of them have an electric vehicle which is charging with a level 1 charger. The demand is 4 kilowatt for each. And in this case, since this transformer has a capacity of 10 kVA, it is overloaded by 6 kilowatts. Animation, please. If we considering equal allocation in this case, because bursts of EV are charging with 4 kilowatts, this overload of 6 kilowatt will be equally allocated to customer A and B. And in this case, this transformer is now within the limit. There's no more congestion issue. To calculate this charging point input limit, there are several minimum data requirements, saying that is including asset utilization, potentially from transformer monitor. So we'll be able to understand what is the thermal congestion happening, and the customer voltages, potentially from smart meters, we'll be able to address the voltage issue. And of course, since we need to allocate the reduction based on the demand, we may need the measurement from the smart EV charger, which might be the extra investment from the customer. The advantage of this limit is quite obvious. It is simple. And since it already been trialed through our different projects, so it is already ready to implement. However, the disadvantage also obvious as only considering electric vehicle, so they might be lacking consideration on other DRs. No orchestration can be ensured. Next slide, please. And now let's have a look on what is happening with this meter level input limit. You can have a very clear clue that saying meter level, now we need to do an equal allocation based on the net demand of the house. In this case, customer A and B, they both have a total demand of 6 kilowatt. And by allocating this overload of 2 kilowatt on top of them, we will see customer A now have a new EV demand of 3 kilowatt. However, in this case, customer B, they do not have an EV need to be charged. It means there is no controllable load in this case. So this 1 kilowatt of overloading cannot be reduced on customer B, which means the transformer will still be overloaded. Moving on. And different from the previous charging point input limit, now we do not need the actual measurement from EV charger. Instead, we will need this customer net demand from smart meter. And it is the beauty of this meter level input limits. It means we don't care about what is happening behind the meter. However, as a cost, as I mentioned, there's a challenging due to the uncontrollable loads and there's a potential violation to the network integrity. However, in terms of how often this violation will happen and to what extent our assets may be affected, we need a more thorough assessment. And maybe because it can happen less often, frequent, and the DSP can still accept it. And maybe this meter level input limit can be an option for the future input management. Moving on, and the last type of the input limit I want to introduce you is a DER input limit. Here we adding more complexity on top of the electric vehicle. In this case, customer B, they have a PV system installed, which is now exporting 3 kilowatt. So in this case, the net DER demand for customer B is 1 kilowatt, and for customer A is still 4 kilowatt. So the overload on the transformer of 3 kilowatt will be proportionally located to A and B based on their net DER demand. By doing so, we can see for customer B, they can actually charge with 3.4 kilowatt, which is higher than the customer A can do. And it is kind of more equitable scenario for customer B because they are now benefiting from their PV installation, the capacity. Moving on. So at this stage, we do not need the meter level measurement. However, we need to know how much the DER the demand is. It can be aggregating by the separate measurement, or you could have a central controller, which is measuring the total, the net demand of the DER. We call it a DER controller or DER hub. And of course, since it's extra devices, we need extra investment in this case. The advantage is, of course, solve the meter level challenge because we are not even trying to control the in-house appliance. What we wanted to control is only those manageable DERs. And of course, it can also help orchestrate all the DERs. Moving on. So let me go through the key remarks to wrap up my talk today. So this is gonna change very soon with the game changer electric vehicle. This demand will surgeon and the flexible input limits are needed to avoid the potential network issues, as you know, the thermal and the voltages. And there are different types of input limits available, which can be adopted depending on different scenario that we need. So today, the charging point input limit is, of course, the most simplest and the easy one to implement, but also like in consideration on the DRs and the meter level input limits. As already introduced in details, there are challenges we need to be aware of. If we can accept the consequence this kind of meter level input limit will bring, we might still able to adopt this input limit. It might still be an option, okay? And in the future, the scenario maybe we will just adopt the input limit of all the DRs or do a per device limit as another option. It solves the challenges, help orchestrate DRs, but just need extra devices. So it really depends on what we are looking for and what kind of challenges we want to address. So hopefully we'll find the answer in the future. Thank you.
Thank you very much, Jing. And before we move to discuss in a few minutes, yes, very interesting things related to investment on operating envelopes and the need for upgrades or augmentation, as it's called here in Australia. So there are challenges. There are challenges in forecasts. There are challenges with the data that is limited, but there are opportunities as well. Again, with the forecast, there's more research that we need to do. There's more work, but there are definitely findings that suggest that we can do much better in terms of data-driven approaches, and particularly in terms of the model-free strategy that Vincenzo was presenting. It is possible with limited smart meter data availability to come up with much better techniques than simplified approaches that are just having a number of considerations because, well, there's nothing more sophisticated to be used. And in terms of flexible imports, as much as everything that we've been discussed have focused largely on export because of solar photovoltaics and the situation in which we are, where actually AER has allowed, distribution companies to offer, the connection agreements for flexible exports. Imports is something that is not necessarily been yet considered as something that can be implemented. So there are trials, as Jing was presenting, and we need to be careful because, of course, it's very different to limit exports, to create curtailment with the solar photovoltaics, but imports are a little bit more complex because this is the electricity that we consume, right? But there are opportunities, as Jing was presenting. All right, so now in the next perhaps 5 minutes, I will just cover two more topics that I believe are important. There's not a lot of time that we can use to discuss, but I really wanted to include them in this presentation and in this course just for completeness. So let's start with the basics. So operating envelopes, I hope that at this stage, in terms of at least exports, we understand that they can increase renewable generation, right? However, as also was mentioned very clearly by Lian, the implementation of operating envelopes is not cheap. All right, there's capex, capital expenditure, there's operational expenditure involved, of course, because of all the IT infrastructure, the data, the extra monitoring, etc. All of that costs money. All right, so how can it be justified by distribution companies? Is a big question, right? Well, let's start with the basics. In Australia, we have what it is called the National Electricity Objective, the NEO, right? That's a website there. And it considers the role of distribution companies in lowering emissions, right? So what is the National Electricity Objective? To promote efficient investment and efficient operation. And apart from different obvious considerations of power quality, etc., reliability, is also, in the ability of the companies to reduce Australia's greenhouse gas emissions or contributing in reducing Australia's greenhouse gas emissions. And that's important, all right? Now, but that is not necessarily saying, okay, how do we justify the dollars, right? So this is the first thing that I wanted just to mention, just because there's a framework that is allowing distribution companies in particular to actually consider their role in reducing carbon emissions, right? But when it comes to dollars, well, there's a method, okay? There's a method. And in Australia, what we have is the Customer Export Curtailment Value Methodology, which is the CECV. All right, in a sense, all right, this value captures the detriment to customers and the market when we curtail exports, when we curtail solar photovoltaics, right? And the idea is that by quantifying that, then you have now a number that can be used to then determine efficient levels of investment, okay? For export services, of course, all right? So let me explain you how it works in a nutshell. So the distribution companies will estimate how much generation is unlocked, meaning by an investment option that is related to facilitate export services. So this investment will allow me to not curtail or to export more, this in megawatt hours. Then they estimate the value of unlocked generation. Essentially, they just use a table. That's the link there, the CECV workbook. It's a massive table for the next 10, 20 years. And it's really for multiple periods during the year. And then that megawatt hour becomes dollars. And then they compare the options, and the highest net economic value wins. Let me show you an example. So let's suppose that the option in a given area is, okay, if we increase the poles and wires, higher cross sections, larger cables and larger transformers, you will unlock generation, right? Because that means that you're not going to constrain. Now, that might mean that you actually are unlocking a lot of megawatt hours in a period, the relative period, 5 years. And that has a value, right? That value is $7 million, let's suppose. However, the cost of having the poles and wires is 10 million. So the net value will be 7 minus 10, minus 3, all right? Now, let's suppose that you go for operating envelopes, a simplified approach. The CECB will say, well, because it's simplified, your estimation is that you're still going to curtail, but not that much. And that means that you're still unlocking generation, the equivalent of $4 million. The cost of this simplified operating envelope approach is 3 million. So 4 minus 3 is 1 million. So the simplified operating envelope already for that regulatory period has a much higher net value than augmentation. Now, what if you go for advanced operating envelopes? Might be more expensive because it's advanced, more sophistication, more data, I don't know. But you are unlocking more generation. So you're unlocking, in this case, 6 million, but the cost is a little bit higher. However, 6 minus 4 is still 2, which is a net value much higher than simplified operating envelopes. Now, I hope that with that, I illustrate. And of course, why would you pick the higher net value? And that's it, really. That's how you justify in a regulated period investment related to exports, to facilitating exports, right? This is, of course, in addition to different other demand-related investments, all right? Population grows, we have many other things that are happening, all right? So I hope that that complements everything. This is how they are doing, all right? Now, to finish, and there were some questions yesterday as well about this, and today, the role of augmentation, really. Larger, more copper on the ground, right? Larger transformers, larger cross-section of conductors, so meaning more copper. And that's what we've been doing for decades, right? That's what we do in every power system around the world. We put larger things because there's more demand. But what happens with operating envelopes? So let's reflect a little bit. These are tables that I extracted from yesterday, from block 2, different operating envelopes, that section. And this is a comparison of fixed export limits, 1.5 kilowatts only, and the ideal operating envelope. The ideal being something perfect that we will never achieve, all right? Very, very unlikely, all right? But still, as a benchmark, it helps. Now, if you look at what I highlighted there in yellow in the first table, what we have here for the different S are just growing number of flexible customers, so on where S4 is much larger than S1. What you have in terms of megawatt hours for the whole day, right, for all the customers, is, of course, the more customers that you have on flexible stuff or with the fixed exports in the different scenarios, the more you are generating, because in the aggregate you have more customers, so you are generating more, all right? And that, of course, applies to the operating envelope. However, let's look at how much it would be in average. In terms of the fixed exports, okay, 1.5 kilowatts, because everyone is being limited. So if you divide 1.6 megawatt hours by 8, which is the scenario 1, it means that it's still, 0.2, which is the same. So essentially, the moment that you actually increase the number of customers is pretty much the same with the fixed export. With ideal, however, you don't get that, all right? The more customers that use operating envelopes, right, the more as a whole, as an area you generate, of course, but per capita, per flexible customer, that number is decreasing. Why? Because the pulsar wires are the same. The limit hasn't changed, and you have many more people to constrain. So the constraint per capita becomes higher. Overall, we're still generating much more, which is great. But per capita, it goes higher. The same thing you can see here on the table on the right, where you have the average export, all right? And that is in kilowatts, all right? What is the difference? So it is actually becoming smaller and smaller, actually, all right? Now, the thing is that, but I really want to highlight here, as much as we've been discussing many aspects of operating envelopes are not a magic one, all right? It's not that they are going to solve all the problems. The more flexible customers, the more solar PV, the less each customer can export. There's no other way around, because the poles and wires are the same, right? So what needs to happen? Well, we need to remember that the aim of operating envelopes is to make the most of our existing poles and wires, okay? This is great because it reduces our electricity bills. The moment that we don't increase, the copper in the ground, it means that that investment is not being made in that regulatory period, and then therefore it means that our electricity bills are not going to go higher. It increases PV generation and reduces our carbon emissions. I mean, we need to tackle climate change, right? So that is all good. However, over time, with operating envelopes and the same pulsar wires, as much as we can have much more generation in the aggregate, we'll have many more flexible customers, but per flexible customer, we'll have less exports. So what do we do? Then that's a question, right? And we need to understand it because that is what is going to happen. Well, what is going to happen is what I call indirect and direct augmentation that will naturally affect exports. What is indirect? We cannot forget we still need to put more poles and wires because population grows, demand grows. We are having the electrification of transport, which is electric vehicles. We're having the electrification of gas. Well, that's not happening everywhere in the world, sure, but it is happening in some parts. So we're moving from gas to electricity. That means more demand. So indirectly, the poles and wires, indirectly in terms of exports, the poles and wires are going to increase, and that will facilitate exports as well. But in some cases, you're right, we will need to put more poles and wires. And it's very likely that even the CECV methodology can justify augmentation because it will unlock what operating envelopes just cannot. All right. So what I really wanted to say here in those few minutes, and then this is where we're finishing this vlog, is that the future is likely to be a mix of conventional and operating envelope related investments. And that's perfectly fine. So don't think that operating envelopes are the solution for the next 100 years. Certainly is not, but they are going to help, and they will help in different circumstances, but eventually we might need some augmentation. Now, with that, we are going to move just for a few minutes to questions, and then we have a little break, and then we'll move to block 3. So there are a few questions there. I'm going to go super quick, and I hope that Vinny, you are ready as well to answer some of them, and Jing as well. So Tim is mentioning here, the baselines do not work at the individual house level. Yes, I mean, that's true. They are not the best to sort of say that one house has the same as the average in terms of a profile and use that as a forecast. That is not necessarily going to match what is going to happen in reality. However, what the companies are doing right now are taking these considerations as an initial step. And as I was mentioning earlier, yes, we need to do better forecasts. But the reality is that if you ask any major company that provide DERMS, distributed energy resources management systems, they have no clue. They haven't ever done it because no one in the world has done operating envelopes as Australia is doing. Distribution companies, they haven't ever done, forecast of voltages or per house active power because they didn't need to. So I think it would be very unfair to say, well, they are doing something that is not that great. Well, yeah, it is technically not necessarily the best, but I mean, there's not many options out there as solutions off the shelf that they can use. So what they are doing is what I consider is very good engineering. And yes, there is room for improvement for sure. There's another question from anonymous attendee, smart meter data to generate a little bit project. Oh, you're referring to the data-driven construction. We can do it with just only smart meter data, and that means that that little portion of the transformer to the first node cannot be mapped, all right? But normally we know what it is. We know that in databases, but if you have the transformer monitoring, you can actually finish off. So actually, most of the network can be done just with smart meter data. Vinny, there's a question for you. Can you answer it?
Yeah, starting from Gary Hayes, right? Do you need 100% of smart meters or can lesser level be used? Well, as I present at the end of the presentation, we have proven that up to 15 to 20%, we can still produce usable results. Of course, there might be less accuracy, but up to 15 to 20%, we're confident to say, and we are investigating for lower penetrations, right? In Tim is asking Vincenzo, is the breakdown of non-flexible and flexible customers valid? Realistically, all customer has essentially inflexible loads. Well, yes, in terms of, I guess there is a confusion in here. When we spoke about non-flexible customers, are those customers that are not subject to the DOE. So for instance, they have fixed export limits as before. And those flexible customers are those that are subject to the flexible export limits or dynamic operating envelopes. So essentially, we are considering the inflexible loads from all customers. As you mentioned in the question as well, we are allocating the flexible capacity to all customers. So this is being considered as you were suggesting in there. So this was answered live. Nasrul is asking, you are doing voltage prediction per customer, right? How do you each node voltage can affect the node voltage without topological information? Well, we are doing voltage predictions per customers, but because we are using historical smart meter data from all customers, the interrelationship between customers are being captured in the historical data. So this interrelationship between customers, the demand in one customer affect the voltages of other customers is essentially encoded in the historical data from past network conditions. So it's being captured by the neural network. Unusual that high voltage occur early in the morning when no PV. Well, yes, that is surprising for me as well. This is not the first time that I have seen it. I don't know if you, Nando, has some comment on that.
Which question, sorry?
From Peter Howe, unusual that high voltage occur in early morning when there is no PV generation.
Oh yeah, I mean, of course, that's called the Ferrand effect. So yeah, this is something that power systems, engineers, our students learn. So the thing is that during early hours, you have very little demand, but so little that our wires, our poles and wires, they can be capacitive, which increases the voltage as well. Not only that, I mean, there might be other considerations as well, depending on how the voltage regulation devices are being used. So not unusual at all.
All right, so the next one, I'm correct in the understanding that model 3 VoltMind derived DOEs does not consider thermal capacity. No, that is incorrect. It considers thermal capacity. We assess thermal constraints at 3 key points in the network, customer connection points, low voltage conductor at the head of the field, and of the distribution transformer. And I guess this is the final for me. This is Tim Vincenzo. MCs are trying to aggressively monetize all data, PQ data. How to make sure that the customer's data, which is needed for their best service, is free? Well, that is more politics than technical. It's not my area of expertise, but in terms of the next question that says, what data has been costing for your trials? We have been working with DNSP, so essentially the data comes directly from them. And with that, the next question is for Jing, I will say.
Okay, got question from anonymous attendee. Is there any proposal to incentivize off-peak charging? Actually, we observe that a lot of people, they subscribe the time of use tariff. So by using that, it's calculated by per meter, the energy usage, right? So EV charging will also be part of your energy usage. So kind of incentivize you to move your charging demand to off-peak hour. There are also other available plan for the EV only, but it's more or less have a higher rate during the peak hour and a lower rate in the solar time. So customer just change their charging behavior. And the other one from Claire, what about V2G at house limit level, export options to store power from EV? Oh yeah, so as a part of export, the V2G definitely need to be considered in this export limit as well. So it is for the flexible export limit will just be as the same as export from solar powers. And next from team, with like 6 kilowatt, we had the subscription level. If that was say 4 kilowatt for house speed, then the DOE signal would require them to turn down. I guess you were saying that if there's a limitation of DOE of 6 kilowatts, 4 kilowatts, so the customer cannot exceed. I don't quite get this question, but yeah, so if there's a limitation on DOE, they wouldn't be able to exceed that level. Yes, okay.
Well, I mean, I guess that the point is, let's suppose that we create a limit that says you cannot import more than 4 kilowatts, but of course, the customer is still importing much more than that. I mean, this is precisely the challenge, of import limits at the connection point. Would you charge for that extra or somehow compensate, or just simply assume that you cannot really tell the customer to manage uncontrollable loads because of course their normal behavior? So that's part of the question. This is not trying to suggest what we need to do or what we need to charge, but there are options, and perhaps the option is to really reflect on the imports from just the controllable loads rather than the whole thing. So it might be different, and there's some food for thought.
Okay.
There's a question there from Lucy. Forecasting requires data, of course, lots of it. How do you collect the data? Well, as they have been doing forecasting for many decades anyways, so with what is available. So companies buy data, weather data and projections of many other things, and of course the monitors that they have. So that's what they do all the time. How will the EV charging stations like other impacts of our networks? Oh, more load, as simple as that. So same principle of what Jing was discussing. So that means that we will need to put more infrastructure.
There's another follow-up by Peter. So apartment and high-rise dwellings will either not have access to individual EV charging. That's true, but they also can install their EV charging in the car park. It's possible. If they do, they will place actually extremely high and concentrated on the net. I guess you were talking about the public charger, like in the apartments, or the users will be able to share those high EV chargers. Yeah, that's true. And similarly, it will put a lot of demand on our MV network and stress our distribution network. Then we have anything else to add on?
No, just that. I mean, just jumping onto the question related to cost, implementation exerts challenges on cost. Yeah, absolutely. And well, I mean, that's what I was explaining with the CCV, Lucy. Now, Tim is asking about the CCV as well. Yeah, I mean, there are limitations with CCV, Tim, but I mean, this is a very good, at least, alternative. Otherwise, if you don't incentivize or provide the methodology to really quantify it, a comparison between options, and incentivize exports, options in terms of exports, then the distribution companies wouldn't do much because they will focus just on demand as usual, as a traditional thing. So it is perhaps not necessarily the best. Actually, if you download the table, there are some numbers that I don't necessarily agree with them, but at least it is a very good starting point. And yeah, there's room for improvement for sure, but still, it's actually pretty decent. I just need to go relatively quick here to the questions. Yes, there are things that we can actually answer offline, and because of the time, we are going to stop here. Thank you very much for all the questions. Just to let everyone know, the next blog might be a little bit shorter because it's really hands-on, and perhaps not all of you have downloaded all the material, but still I will go through this just so it is recorded and you know what is the content that it is available there. So for now, thank you very much, everyone. And again, thank you to the University of Melbourne, of course, all the support, Jing, Vinny, C4Net, and Pre-Gauge and OSNet as well, because of the different things that we were doing with the forecast and the data-driven stuff. That's what we're thinking then. Thank you very much. And then we will have just a couple of minutes of break. Thanks.
And I will